Hello everyone, my name is Eduardo and today I'm going to present you my final project for EEL 6825 Pattern Recognition course in the University of Florida. The name of my project is Automatic Modulation Classification using Deep Learning. Here we have the agenda where we will have a brief introduction about the problem that we're trying to solve and some background. Next, we will discuss about the related work, such as the published papers and methods that were discussed about the automatic modulation classification problem. In the method description, we will explain the study proposal and also explain how we have implemented our convolutional neural networks and the data set that we have used. In performance evaluation, we will have a showcase of the results, including the key performance indicators, and finally the conclusion and future work. As an introduction, we have new connected devices and systems that has been deployed in the field utilizing wireless communications techniques. Most of those techniques utilizes the adaptive modulation, where there's a change of the modulation type in order to enhance the demodulation performance. So as a consequence, we have different types of modulations being transmitted over the air in the field. Some examples are Internet of Things devices and in-man aerial vehicles, UAVs, that could utilize wireless technologies or standards such as the 3GPP, 5G new radio, and our technology. Cognitive radio or CR systems utilizes the optimal modulation type based on channel conditions, and as a consequence the receiver must dynamically detect the modulation scheme used. So the problem here is how we can obtain the modulation type in the receiver if we don't have the prior knowledge of what is the modulation type that the transmitter is using. Well, one of the solutions is the Automatic Modulation Classification, AMC, where without prior knowledge of the DX modulation, we apply some techniques to automatically identify the receiver modulation, and usually we also use software-defined radio SDR for this. Some common applications are military, regulatory, or commercial applications for spectral sensing and monitoring. Here we have a block diagram for a wireless communication system in figure 1, and the most important part here is to understand that all data that we send over the air has to go through a modulator, and basically the modulation is a technique to transmit data in a wireless channel by utilizing the RF physical waveform parameters such as the waveform amplitude, frequency, and phase. After we send this information over the air using a modulation type, the data is received in the receiver with some distortion from the channel, and then the demodulation process is applied, which is the inverse technique for modulation process. We have two types of modulations, the digital and analog modulations. Basically, for the digital modulation, we utilize discrete time domain techniques to encode data. Some examples are the creditor amplitude modulation, or QAM, that is also used in 3GPP technologies such as for the 4G long-term evolution or 5G new radio technologies. For analog modulations, we apply a continuous time domain technique to transfer data and send it over the air. So some examples are the FM frequency modulation, which is used in radio stations to send music and speech transmissions. Here we have the IQ representation of the received signal. Basically, in figure 2 we have an illustration where we have two signals, the IQ, the I signal, which is represented by the sine signal, and the Q, which is represented by the cosine signal, illustrating the concept of the IQ samples in time domain representation for each modulation. And in figure 3 we have the same representation in the constellation diagram in this case for the QPSK modulation. Deep learning is a field inside machine learning where it consists of a neural network architecture where we have several layers, where we start with an input, some amount of hidden layers and an output. Each layer contains an input and output involving an activation function with corresponding learning weight and bias that can be represented as y, which is the output, equals the input x times the weight plus bias, if any. This category can be also divided between supervised, unsupervised, and semi-supervised learning. In this project we are using the supervised learning approach, and the deep learning can also be applied for feature extraction and classification, which can be applied to the AMC problem. Related work in the AMC fields is regarding the likelihood method, which here I mention use work. Basically, likelihood method is a high accuracy method, but the problem is that it requires high complexity in the design and also requires some prior data set information, in our case prior TX modulation that were received previously. So this is not something that we typically have. And we have the feature extraction method, which is also described in Soliman work, where we apply a feature extraction method that we no longer need to have prior data set or prior modulation type information in order to predict the modulation type that is used in the transmitter. And also an advantage is that it doesn't need to have such high complexity design when compared to likelihood method. One of the most important works in AMC using deep learning is O'Shea work from 2016, where he proposed the use of a convolutional neural network as a feature extraction method for AMC problem, and then utilizes a classifier to classify what type of modulation it's being used. So basically we can use a CNN to extract features and patterns from a given input, such as an image. And in the case of IQ samples, we can also represent the IQ samples as a two-dimensional image, where I is the first dimension and Q is the second dimension. Here's also the representation from O'Shea work in figure 4, where we have his proposed convolutional neural network, CNN, where the input is a 2 by 128 IQ sample, and then we have the feature extraction occurring at the 2 convnets, where we have the ReLU activation function. So in his work he utilized 64 filters for the first convnet and 16 for the second convnet, with a respective kernel size of 1 by 3 and 2 by 3. Then this is connected to a dense layer, and from the dense layer we have another connection to a softmax, where we are going to generate the probability distribution for each class, in our case the 11 modulations, and then we will have the probability of each modulation in the output, and we can easily predict what type of modulation is being used in the transmitter when we receive the received signal. Now we also have 2 more works which is more recent, from 2020. The first one is from Musman, where he also utilized the CNN architecture, but his focus was more in the low-powered IoT devices, so not just the accuracy but also the system complexity had to be considered as well, and he utilized the separable CNN in his architecture. And the other work is from Hermawan, where he proposed a CNN architecture where he utilized several convnets but with a small number of filters to reduce the computing time, and also applied a Gaussian noise layer to reduce the overfitting. What's interesting about this project is that the latency was also one of the key performance indicators, because it can be used for critical latency applications for beyond 5G communications. For the method description, we have our project proposal here, where we have designed and implemented 3 CNNs with the purpose to achieve the best trade-off between accuracy and system complexity. The 3 CNNs has been submitted to the same training parameters, and I have utilized Python 3.6 with Keras and TensorFlow modules to implement the neural network. I also utilized the GPU training with the NVIDIA GeForce MX 250. The dataset that we have used is the open dataset Radio ML 2016.10a. This dataset is available in the reference section for this presentation, and basically consists of synthetic signals generated from the GNU radio, where we have 11 modulations, 8 digital and 3 analog modulations. There's a total of 220,000 data samples, including a variable SNR dataset from -20 to 18 dB, and each data sample contains 128 time domain IQ samples. So the CNN training parameters that we have used for all the 3 CNNs are 100 epochs. We utilized the ADAM optimizer using a learning rate of 0.005. The dropout of choice was also 0.5 based on some trials and errors that we have fine-tuned the parameters. The training batch size was 1024, and 80% of the dataset was used for training and 20% of the dataset was used for testing. Here's the CNN1 architecture, where we call the ConvNet model. So basically the input is the 2 by 128 IQ samples, and then for the feature extraction we utilize 2 convnets with the ReLU activation function, where we utilize 256 filters for the first convnet and kernel size 1 by 3, and in the second convnet 80 filters with a kernel size of 2 by 3 and then connected to the dense layer. And for the classification we have a 256 input dense layer connected with the ReLU function, with another connection to a softmax, where we have the prediction for the 11 classes, which in this case is the modulation. And the design complexity for this architecture is 429,403 parameters. For CNN2 we also have the same input, but now we are also applying the separable convnet. So for the feature extraction we have now 2 sequential convnet connected to a separable convnet with ReLU activation function, where in the first sequential convnet, separable convnet connection, we have 256 filters, and for the second sequence we have 256 and 18 filters applied. For the classification we also have the same concept as the previous CNN one, but the difference here is that we're using 80 input in the dense layers, so we can connect to the softmax layer with the ReLU activation function, getting our 11 classes output. The design complexity of this CNN is 385,307 parameters, which is lighter than the CNN1. For the CNN3 we have a proposal where we have a convnet utilizing max pooling model. So as an input we also have the IQ samples 2 by 128, but now we have some sequential convnet with ReLU activation, where we have two sequential convnets, including a max pooling output, and this max pooling output will help reduce the size of the output in order to try to reduce the complexity of our design. And if you see in figure 7, we also have the details of each filter and kernel size that we have utilized. As you can see here, we have a total of 4 convnets being utilized, and for the classification we also use the same 80 input in the dense layer, same concept as for the CNN2, and we have a design complexity of 310,603 parameters, total parameters. So here we have the results for our project. So basically in figure 8 we have the illustration of the accuracy against the SNR. So as you can see here in the orange line for CNN2, we had a good accuracy for the good SNR conditions from 0 until 18 dB, where CNN2 outperformed the other CNNs, but in low SNR conditions CNN1 outperformed the other CNNs, and all the CNNs had low performance below 10 dB SNR conditions. During the training of the 100 epochs, we noticed that CNN1 did not have any overfitting, while CNN2 and CNN3 had some overfitting starting from epoch 10 onwards. Here's the confusion matrix for each of the SNR conditions. In this illustration we have the confusion matrix for 18 dB SNR conditions, where the accuracy was respectively 66.20% for CNN1, CNN2 69.21%, and CNN3 66.57%. So as we have shown in the previous SNR accuracy plot, we have the CNN1 with the better performance in good SNR conditions. For low SNR conditions, we have the confusion matrix here, including the -4 dB scenario, where we can see that CNN1 outperforms CNN2 and CNN3 with an accuracy of 50.56% when compared to CNN2 48.49% and CNN3 46.63%. And for the worst case SNR conditions, which is the -20 dB, we can see that all the CNNs had poor performance and the accuracy was below 10%. So to conclude this work, we have defined and implemented 3 types of CNNs in order to identify the model with the best accuracy and complexity design trade-off. Since the results show that the CNN2, which utilizes the separable convnet, had less complexity design, at least in the number of parameters when compared to CNN1, and had better accuracy than CNN3 with lower complexity design, we can conclude that CNN1, CNN2 had the best accuracy and complexity trade-off design. For future work, we should consider modifying the input data set and check if we're able to filter the data set for positive only SNR, and also have another experiment with negative only SNR and check if we have any performance enhancement in the line of 0 to 20 dB, 0 to 18 dB, and 0 to -20 dB. Also, due to the lack of time, we couldn't do many adjustments in the number of filter and kernel size, so for future work it should be important to also consider the optimal trade-off configuration between accuracy and complexity for each of the convnets. And another interesting point here is that since we had low accuracy under 10 dB, minus 10 dB SNR conditions, we should consider to investigate how we can obtain better accuracy in the CNN architecture using low SNR conditions. Here we have the reference that we have used for this presentation, and I would like to highlight that here in reference number 6 there is a web link from DeepSeek where you're able to download the data set that we have used for this project. So now we're going to do a code demonstration. So here we have the code that we have used. Basically, we have used the main source code, which is the AMC_DL_code, which is the main file that we ran on Python. And we also have a complementary file, which is the CNN_model, where we declare CNN 1, 2, and 3. And as our input data set, we have this pickle file, which we have obtained from reference number 6 from the presentation, where we load the data set into our neural network. So before we get into the main code, let's just have a look at the CNN model here. So when we look at this Python file, we see that we have the declaration for our three CNN models. So we have the CNN 1, 2, and 3 declared here. Each CNN has some parameter functions. The first one is the batch normalization. The second one is the activation function, which in our case is the ReLU. The inputs, which is the data set, the dropout, and the classes, which are the modulations that we have used. So now let's go into the main code, and here we have the step-by-step. So the first step is we load the modules, especially the Keras and TensorFlow. And since I'm using a GPU, I also add the GPU configuration. If you don't have a GPU, you can run on your CPU as well. Here we load the dataset based on the pickle file. And this dataset is then loaded into a dictionary file where we have the modulation, the SNR, and also the 2x128 IQ samples. Here we configure the training rate and dropout rate. So basically I'm using 80% training rate for my neural network, and the remaining 20% is going to be for testing. And the dropout rate that I utilize is 0.5. So here we have a print of the total training sample that we're going to use, which is the 80% samples, and the IQ samples, which is the 2x128. And here we have the declaration of the first CNN. So we declared the SIG model variable as the CNN1 from CNN module that I just showed you previously, and then we declared the function batch normalization as false. As an active function, we're going to use the ReLU. The input shape is already declared previously. The dropout rate of 0.5, which was declared here, is also included. Then the classes is the 11 modulations that we're going to use. We also utilize the Adam optimizer with a learning rate of 0.005. And to represent the loss, we use the categorical cross entropy. And we used a total of 100 epochs and a batch size of 1024. And after you run this code, you will get this output for the CNN1 and the total parameters as well. And then we perform the training by running this code. We can also save the training performance in this H5 file, and then when we run the code, we will see the number of epochs occurring. It took around 8 or 9 seconds depending on the epoch, as you can see here. And then after some epochs we reach 100 epochs here with the value loss and the value accuracy and the total accuracy here. So now we can plot this data. So here we have the training performance. We don't see any overfitting occurring. And then we plot the confusion matrix. So the output of the confusion matrix is going to be here. We have the average confusion matrix, and then each confusion matrix for each SNR level from -20 until 18. And we also have the information, the total accuracy per SNR level. So for -20 we have, for example, 8.86%, and for SNR 18 we have an accuracy of 66.20%. And now we can also plot the accuracy versus SNR plot here. And this is the end of CNN1 test results. So for CNN2, it's very similar to the CNN concept, but now we just change the function here to CNN2. The parameters are identical because we're using the same conditions between all CNNs. Here we have the output of our CNN. We perform the training, and then we have the training until 100 epoch. We plot the training where we see the overfitting. We obtain the confusion matrix, and we also obtain the accuracy per SNR level. For the accuracy and SNR plot, we also have here for CNN2. And now for CNN3, we have the CNN3 load here in our function. We have the output again. We perform the training from epoch 1 until epoch 100. We plot the curves, and we also see the overfitting occurring in CNN3. We plot the confusion matrix, and we also have the accuracy and SNR values here. And here we have the accuracy and SNR plot. So this is my presentation. Thank you very much for watching.